Hello, welcome to Management Science Studio. I am Bahid Lotfi and I'm an emeritus professor of management science. In this video, I will demonstrate how to solve the production planning problem using a linear programming approach. So let's get started. Recall the problem we were trying to solve was a firm is about to develop its production schedule for the next 4 quarters. The production manager had obtained the relevant data consisting of demand forecast, regular time production cost, unit inventory carrying cost per quarter, setup cost for each of the next 4 quarters as shown. The production capacity was unlimited, overtime and subcontracting was not allowed. These were our parameters. For the 4 quarters, the demands were 100, 120, 130, 150. Unit production costs were the same at $10 per unit. Inventory carrying costs or holding costs were the same for the 4 quarters at $2 per unit per period. Setup costs, however, were different. For the first period, or setup in the first period is 200, second period is 300, third period 300, and the last period is 200. And of course, again, no overtime, subcontracting, or stockouts were permitted. And we assumed there was no capacity limit. If you recall, we used 3 heuristic procedures to solve this problem, and the resulting total cost were in the heuristic where we only used one setup and produced everything in first period. The total cost was 6,850 units. When we used level production strategy, the total cost came to $6,160. And when we used demand chase strategy, the total cost came to $6,000. And again, we do not know if in fact any of these heuristic solution procedures has resulted in an optimal solution. So now we are going to use linear programming formulation to solve the same problem. First, let's look at the formulation. In order to develop our linear programming formulation, we must first define our variables and constants. So we start with the production variable. We let xt equal to the production amount in period t, and we have 4 quarters, so t goes from 1 to 4. I sub t is the inventory at the end of period t. Z sub t is a binary variable. It's equal to 1 if we produce in period t and 0 otherwise. This variable is used to incur the setup cost. Our constants are d sub t, which is the demand in period t, c sub t, which is the production capacity in period t. We set this to a very large number for unlimited capacity. P sub t is per unit production cost in period t. H sub t is per unit per period inventory carrying cost in period t. And S sub t is setup cost in period t. So, our problem formulation. We want to minimize the total production, inventory, and setup cost. So, we'll minimize summation t going from 1 to 4, p sub t, x sub t, plus summation t going from 1 to 4, h sub t, I sub t, plus summation t going from 1 to 4, s sub t, z of t. And we have constraints. The first set of constraints are demand constraints. So that is d sub t, which is a demand in period t, is equal to x sub t plus I sub t minus 1 minus I sub t. That is, the demand in period t must equal to production in period t plus the end inventory from the previous period minus the end inventory for the current period. And we have our capacity constraint. So x sub t must be less than or equal to c sub t multiplied to z sub t. So if x sub t is positive, it will force z of t to equal to 1, and then we will have a setup cost in the objective. And lastly, our non-negativity constraint. So x sub t and I sub t are real, greater or equal to 0, and z sub t is a binary variable equal to 0 and 1 for t equal to 1 through 4, and we must make sure I0 is equal to 0, that is the inventory in the beginning inventory. This problem, however, is not in the standard form. As we can see, constraint set number 1, which are the demand constraint, the constant is on the left hand side, the variable is on the right hand side. So we have to interchange them and make sure that the variables are on the left hand side, the constraint, and the constant is on the right hand side. So we rewrite that as x of t plus I sub t minus 1 minus I sub t is equal to dt for t equal to 1, 2, 3, 4. Similarly, the second set of constraints, the capacity constraints, again, a variable zt is on the right hand side, it has to be on the left hand side, so we rewrite those constraints as x sub t minus c sub t multiplied to z sub t less than or equal to 0 for t equal to 1, 2, 3, and 4. Now we are ready to go ahead and look at our linear programming solution using the solver. I have set up the linear programming model to be used with solver in this worksheet. If you're unfamiliar with how to use solver to solve linear programming problems, please visit Management Science Studio and watch my video on how to use Excel solver. So our variables are up here in the second row, starting with the production variables x1 through x4, the inventory variables, and we have the I0, which is the beginning inventory, and I1, I2, I3, and I4, and then our set of variables that are z1 through z4. My objective function value will be stored here, and the objective function coefficients are here. The first 4 relate to the production per unit cost, which are 10. The second numbers are the inventory carrying cost. If you recall, they were $2 per unit per period. The last 4 numbers are the setup costs that were 200 for period 1, 300 for period 2 and 3, and 200 for period 4. And of course we have our constraints. The first 4 are the demand constraints. So it's x1, you see a 1 here, x1 plus I0, which is the beginning inventory, minus I1, inventory at the end of period 1, must equal to our demand, which is 100. Similar situation for the second period. x2 plus I1 minus I2 must equal to 120, and so on. Now we go to the capacity constraint. The capacity constraints are x1 must be less than or equal to s of t z of t. I have chosen 1000 for the value of s of t, which is being multiplied to z1 for the first period must be less than or equal to 0. Similarly, for the second period, capacity constraint number 2, x2 minus 1000 z2 less than or equal to 0. Third period, x3 minus 1000 z3 less than or equal to 0, and so on. And finally, the last constraint, we must make sure that we force I0 to 0, otherwise everything will be produced in the first period or the initial inventory. So we can see that I sub 0 is going to equal to 0. Now, as usual, we have our objective function value here. Let's take a look at the formula. This is the usual sum product formula that is multiplying the objective function coefficients to the decision variable values that are stored in this row here. Okay. Similarly, our uses constraint, as before, we can see that this is the sum product of the constraint coefficients in the first constraint multiplied to the values of the decision variables, and that's our uses for the first constraint, and the other constraints are similar. Okay, now we are ready to use the Excel solver. So we go to data, select solver. Now we have to enter our parameters. So the solver parameters are objective function value is stored here, so I set that. I want to minimize, I select that. By changing the variable cells, or decision variable cells are here, so I'll go ahead and click on here and highlight the decision variable cells there. We can set that. Now we have to add our constraints, and our constraints, the first four, the relationships are the same, so I can actually highlight them. The set references right here, the first four, because they're all equal to the right hand sides, which are here, and that's our first set of four constraints. Now we'll go ahead and add the next set of constraints, four constraints. We'll go ahead and highlight the next four, which are here, right there, and the relationship less than or equal to the right hand sides. And we add the last constraint, which is the initial inventory, and that is stored here, and the relationship is equality, and the right hand side is 0. Now we have to add one more set of constraints, and those are the binary variables z. So we'll go ahead and add one more, and this time I'll select the values in the z for the z variables, and the relationship I select is binary, and I don't need the right hand side, and just click OK, and my linear programming formulation is complete. I can go ahead and solve, and you will see that solver produced a feasible solution, reached optimality. We'll click OK, and now we'll discuss the solution. We can see that solver produced 220 units in the first period. The demand was 100, so 120 units were carried as inventory. So let's take a look at I1. The value of I1 is 120. Notice that I0 went to 0 because we forced it. And because we produced in the first period, Z1 should be equal to 1 so that we can incur a cost of 200 as setup cost. We go to the second period, we don't need to produce anything because we carried 120 inventory, so x2 is equal to 0. Notice that z2 is going to be equal to 0, and we will end up with 0 as I2, which is the end inventory in period 2. We go to period 3 and we produce 130 units, so z3 is equal to 1. We incur a cost of $300. End inventory in period 3 is equal to 0. Finally, in period 4, we produce 150 units, z4 is equal to 1, we incur a cost of 200, and our end inventory is going to be 0 for a total cost of $5,940. Now let's compare this cost to the total cost that we received by using heuristics. So we go to the heuristic solutions, and we can see that the three heuristic solutions, the least cost solution was 6,000 associated with the demand chase strategy. So the linear programming formulation produced the optimal solution at the minimum cost of $5,940. Now let's say our problem is capacitated and the production capacity for each of the 4 quarters is 130 units. So we'll see what happens. In order to solve this problem, all I have to do is to change the 1,000 that I used in order to incur a setup cost to 130. So I'll make this 130, 130, 130, and 130. And we'll go ahead and use solver again. Notice I don't have to change anything. All I have to do is to solve the problem one more time. And solver produced the feasible and optimal solution. And here are the results. In this case, solver produced 110 units in the first period. So the demand was 100, so it's carrying an inventory of 10 units in the first period. It produced 130 units in the second period. Demand was 120. We already had 10 units, so it must carry 20 units in the second period. For the third period, it produced 130 units, and we had 20 units, so we have a total of 150 units. and we only used 130 units. So at the end of the third period, I carried 20 units of inventory. And finally, in the fourth period, it produced 130 units. These 130 units are obviously our capacities in these quarters. And with 130 in the fourth quarter and an initial inventory of 20 units, that is our demand of 150 units. Now let's look at the setup variables. Because we produce in every one of the four quarters, we are incurring all of the setup costs. So Z1, Z2, Z3, and Z4 are all equal to 1, forcing the setup cost to be incurred. And this time the total cost went up to $6,100. And that is how we solve a single item multi-period production scheduling problem, either capacitated or uncapacitated.